Yeah, so today we're going to talk about holomorphic maps between Riemann surfaces and show a kind of structure theorem for them. And the point is somehow, I mean, because the Riemann because being holomorphic is at least in one complex dimension is pretty flabby. We'll see that essentially we have a very nice local structure theorem for holomorphic maps. And what that's going to do is it's going to say that essentially all of the information in a holomorphic map between two Riemann surfaces is really encoded in some combinatorial information, which actually allows us to say some very nice things about how one can construct holomorphic maps. So let's get started. Right, so we're going to first just make the following lemma. Just recall this. So this is a kind of holomorphic inverse function theorem, which we'll use in a second. But so the idea is, let's say we have this is just a complex analysis fact. Suppose we have a map U and V, but this is holomorphic. And U and V are neighborhoods of 0 in the complex plane, and we're going to assume f of 0 is equal to 0, and f prime of 0 is not 0. So all of this is supposed to imply that there exists a smaller neighborhood of 0 such that is a biholomorphism. Okay? And so the proof of this, so there's sort of two, I mean, the easy proof in a sense is, as Hayo mentioned last time, and probably in his first lecture too, I mean, you think of this complex valued map as an R2 valued map, and then this condition tells you that the Jacobian of the map is non-zero, and so then you can use the real inverse function theorem to say that there's a smooth inverse, and then you can just use the chain rule to prove that it's actually holomorphic. So this is followed from the real inverse function theorem. Equivalently, you could try and adapt. Remember, we had this lemma last time where we were able to study solutions of equations of the type f of z w. So if you just take this as equal to w minus f of z, you can try and adapt the proof I gave last time to prove that this inverse function theorem. Okay, that being said, the reason we care about this is the following sort of observation about what happens for functions when we don't have that are holomorphic and non-constant when the derivative at 0 is allowed to be 0. So this is another lemma. So let's suppose, again, let's suppose f takes u to v. So u, v, open neighborhoods of 0 in C. And now let's assume that, again, f of 0 is equal to 0, but also this is f prime of 0. And let's assume this is non-constant, because if it's constant, there's nothing interesting to say. Okay, so if we assume this, the point is then there exists an integer k, which is bigger than or equal to 1, and a holomorphic function g that takes a u prime to C. So here we again have 0. It's a neighborhood of u prime. And then the upshot is that f of z is equal to g of z to the k. And of course, this would seem trivial if we just took k is equal to 1 and f is equal to g. So the point, though, is that g prime of 0 is not equal to 0. Okay? Okay, so what we'll see is, of course, when we work on maps between Riemann surfaces, we'll be able to use this to give a very nice local description of all holomorphic maps. But before we do that, let's just give a proof of this, just because it's simple. Okay, so let's just prove this. Okay. So the point is f is not non-constant. Right, so it's not identically 0. And that tells us by just a kind of, again, standard kind of power series expansion that f has the following form, which is it's right, this is a kind of Taylor expansion. And the point is AK is right. And of course, I mean, we could do this for smooth functions, except for a smooth function, we wouldn't be able to say that k, we couldn't assure that AK was that k was finite, right? So here k is a finite integer. And the idea is basically, if this was not possible to do, then f of z would vanish to infinite order at 0. And that would mean it had to be identically 0. So that's where the holomorphic comes in. But now, once we do that, right, we just rewrite this as equal to AK zk times 1 plus z f tilde of z. And f tilde is, of course, a very nice function. So the idea is if we make z very small, this is going to map. This guy will be very small, and so this part of the function is going to map into a small neighborhood of 1, right? So this maps to a small neighborhood of 1. Right, and of course, if we just take, 1, if we do a branch cut on, say, the negative real axis, that allows us to take the kth root of this function in a well-defined way. So we let h of z equal to the kth root of right, and obviously, this is not globally defined, but it's certainly defined in a neighborhood of 0 precisely after we make a choice of branch cut. Okay, so then if we just take k, the kth power of this, the idea is we can just write g to be g of z now is equal to ak to the 1 over k, where this is just a non-zero complex number, so this is just some choice of root, which we have k possible choices, so we just make 1. Then we multiply by z, and then we multiply by h. And it's easy to see that if we take this to the kth power, we get back to f. And the point is, if we compute the derivative of this guy at 0, then if the derivative lands here, we get 0. But on the other hand, if the derivative lands here, we get h of 0, which you can see has to be 1. So we're done. Okay? Okay, so that proves this complex analysis lemma. But the point is, this allows us to prove the following fact, which is this kind of local structure for a holomorphic map. So let x and y be, say, connected Riemann surfaces, and let's say f between x and y is holomorphic. Then for each x belonging to x, there exists a unique integer kx, which is kx, and charts, say u phi about x and phi psi about capital F of x, such that basically such that if you consider the function f in these charts, so we look at psi composed with f composed with phi inverse. Sorry, this is a function on some domain neighborhood of 0, and this is some. Let's assume phi of 0 is equal to 0 is equal to phi of x. Right. So they're nice charts. So then this is supposed to map 0 to 0, and essentially just applying this theorem to this, we see that we can change charts so that in fact this has the following standard form, which is that it's z to the kx. Okay. Right, and the proof of this, which I'll just maybe say in words because it's it should be pretty clear to you, is basically you pick any charts with these two properties, then you look at this function, and you can see that this function satisfies the hypotheses of this lemma, and so then you use the function g of z, which, because the derivative is non-zero, is actually a biholomorphism. If you shrink domains a little bit, you use g to change the chart psi, and then you'll get so that in this new chart, you actually have this structure. Okay? So you should work that out for yourself if you're not familiar with, but it's straightforward. Okay, so this is pretty nice because, right, I mean, it tells us that basically if we're looking at least locally for any holomorphic map, there's only essentially one piece of information we need to keep track of, which is this integer, or this non-negative integer k of x. So as a note, which this is just a note, but right, this implies a corollary of this, which you should again maybe just check yourself, is that if f take x to y is non-constant and holomorphic, then it's an open map. Okay, so this is obvious at points where k of x is equal to 1, because obviously it's just a local. You should check it's a local diffeomorphism, and you have to do a little bit more thinking when you're at a point where kx is strictly bigger than 1. But again, it has to do with the nature of this map, right? So you should convince yourself of this. But of course, this has very useful consequences because it says that, for example, if this guy is C instead of Y, and you take the real and imaginary parts, then neither of those can have interior maxima or minimum, which is quite useful to know. Okay, and as I said, once we have this, once we have this function f, we're going to often think of this k as a kind of function from the space x into the non-negative integers. Okay, so an interesting thing about this, one of the useful things about this kx is it has a certain, there's a certain topological information that's encoded in it. So to make this crystal clear, let's assume, we'll make the following assumption. So from now on, we're going to have these maps between connected Riemann surfaces as before, is a holomorphic map. But we're going to assume it's also proper. right? So that just means that the inverse image of a compact set is compact. So under this assumption, we're going to make the following definition, which is we're going to define this number called maybe the local degree at the point y, which is going to be the sum over x in the preimage of y of k sub x. Okay? So the importance of this assumption that the map is proper and it's non-constant. So the importance of this assumption that it's proper is that that's going to make this a finite sum. Okay, so you always have to be a little worried when you're summing over something that your sum makes sense, and the point is this is going to be a finite sum, so it will make sense. To see that it's a finite sum, well, first of all, the preimage of a singleton point is certainly a compact set by the properness. So the question is, why is a compact subset of X a finite set? So the reason that's the case is, of course, and you should convince yourself of this, of course, but it should be pretty clear. I mean, the point is the preimage of a given point should also be a discrete set unless you're constant, right? Because otherwise, if you had a point of accumulation, you can go just look in a chart and use the kind of usual complex analysis arguments to say that if you had a point of accumulation to this set, then actually the function f would have to be identically equal to y. Okay, so the point is this set is discrete and compact and hence finite. Okay, so we have this d of y, and the sorry. No, I'm not.
So why would there be a point of accumulation of a finite set?
Well, I'm assuming the map is proper. So I'm saying the preimage is a compact. That means the preimage has to be compact.
Oh, okay.
So if it's not discrete, then there would be a point. I mean, the definition of discrete means there's no point of accumulation. So, or, I mean, it's certainly a closed set. So. Okay, so the point now is that we have this integer d, but the sort of claim, which is the relevant topological claim, is that actually this integer d of y is independent of y. Okay, so in other words, this is just this integer is an invariant of the map and not of the point y. Okay, and so we just make a remark. So actually, this invariant seems to be a kind of holomorphic invariant in the sense that we use the kind of Riemann surface structure to define it, but if you work a little bit harder, and you can more or less convince yourself that this is actually a topological invariant. So this d is the topological degree. Right. Okay, so where one has to make sense of this, but the idea is it has nothing. In this case, it has nothing. The value has nothing to do with the fact that everything is coming from this Riemann surface setting. Anyway, so what's a proof though? Let's give a proof. I mean, we have all this extra structure. We might as well use it. So the point is that if we just consider a very simple setting, which is the map. If we consider the map that f, which takes the say the unit disk to the unit disk, which is the map z goes to z to the n, right? Or maybe it's better to say z to the d. Right? It's clear that d of y is identically equal to n, right? So if we're at 0, then k sub 0 is d by definition. And otherwise, if we're not at 0, then there's exactly d roots of roots. And so then we have k at that other point is 1, but there's d of them, so the sum is d. Okay? But now the point is, right, in general, the properness of f implies that there exists a neighborhood v of y such that d, yeah. Okay, so the point is we can pick a small neighborhood v of y so that we can actually apply this preceding proposition to each component, such that we can apply this structural proposition, the star. Let's call this star to each component of right. So since we can apply star to each component of V, then we can compute in each of these components of the preimage, we can compute we can see that the degree is locally constant, and then hence actually the degree is locally constant in V if we add everything up. So this implies that D is locally constant. Right, but it's locally constant, and we're assuming y is connected, so if we have a locally constant function on a connected space, then it has to be constant, which is the claim. Okay, so this degree D is going to be quite useful in sort of analyzing, well, if we have two maps between, say, Riemann surfaces, two holomorphic maps, in general, if the map, it doesn't need to be one-to-one, and so then what can happen is the genus of the two maps can be different. But what you'd expect is there should be a relationship between the degree and the genus, and so that's one of the things that we'll get to, but the genus of the two maps and the degree of the map, but and some other information. Okay, so let's move on from this to just use this to make a kind of simple observation, which actually would be very kind of key to our proof of. It's sort of a key idea in trying to prove the uniformization theorem, at least the approach we're going to take. Okay, so just first the definition. So so Hayao defined a meromorphic function on a complex manifold of higher dimensions, and of course it was fairly involved. But as he pointed out, on a Riemann surface, it has a pretty simple definition. So we say a map F that takes a Riemann surface X to S2 is meromorphic. So a holomorphic map. Is meromorphic. That's the definition of meromorphic. So if we want to talk about meromorphic functions on a Riemann surface, we just consider them as holomorphic maps into the Riemann sphere. Right? So none of the sheaf theory is needed. And the point is and it's not, though we don't want, which is not, let me just put a technical mark, which is not. So we don't want the map that maps everything to infinity. That should not be considered a meromorphic function. So the point is, right, the poles, of course, of F are the preimage of the point infinity. So by assumption, they're not everything. And the orders of a pole is k sub x for x, the pole x, is the value k sub x. So I'll leave it to you to check that this, when x is an open domain and in the complex plane, that this agrees with the usual notion of meromorphic. But the upshot of this, together with our proposition over there about the degree, is the following nice way of characterizing the Riemann sphere, which will hint at how one can sort of try and approach the uniformization theorem. So we have the following sort of, let's say it's a corollary of the proposition. So if x is a compact connected Riemann surface with a meromorphic function f that takes with one pole of order 1, then this implies that x is equal to the S2. Okay? So in other words, if we wanted to sort of prove that a connected compact Riemann surface was the same as the Riemann sphere, one way of doing that would be to try and construct a meromorphic function with a single pole of order 1. Okay? So this is I mean, one needs, of course, some theory to guarantee the existence of such a thing, but that's sort of the spirit of what we're going to prove in the next week will be how to kind of see why such a thing might exist or not exist using sort of PDE type methods. Okay, so let's just give a proof of this. Well, maybe I'll just say it in words, right? So the proof is just very easy from the proposition. So the first thing is, of course, x is compact, so the map F is automatically proper. So we can apply the theorem. And the fact that you have one pole of order 1 means the degree of the map is 1. So that means that at every point, there's only one element in the preimage. In other words, the map is 1-to-1. So it's 1-to-1, and as we saw, it's open. So it's open, and in 1-to-1, it means it has to be onto as well. And so then so that you can construct an inverse. And then the point is, not only, I mean, again, because we know by definition that k of x at each point is 1, again, by this fact, that means that, in fact, you should check, that means that, in fact, we can apply the inverse function theorem to see that it's a local diffeomorphism, and hence the inverse is actually a diffeomorphism. But then we can just use the chain rule to see the inverse is a holomorphic map. And hence this map F gives us the identification between the two things as Riemann surfaces. Okay, so the proof is, I just said. Okay, so that being said, let's switch gears a little bit and maybe try and use this degree to try and study some of the global properties of this function f that's holomorphic. And as I said, right, I mean, locally f there's only one sort of invariant that determines the behavior of f, which is this integer k of x. So what that should tell you is that really the only information that really should determine f is some kind of combinatorial information, which is how to put together the pieces. So let's see how to kind of make that precise. Using a sort of theory of covering spaces. Okay, so from now on, okay, so we're assuming that we have a function f to x to y, which is holomorphic. Now we're going to assume y is connected of course, these guys are Riemann surfaces. And we're going to let D be the okay. Okay, so that being in the setup now, we want to kind of look at the a kind of distinguished set of points, which are the points where f has a branch point, right? So or a ramified point. So we're going to define R to be the set of x in X, and non-constant as always. So we're going to let X be the set of points in X where Kx is strictly bigger than 1. Okay? So you should check that R is discrete, as is what's called delta, which is the image of R. Okay? So I'll leave that as an exercise. Just again, the reason this say is discrete is because, of course, these points are exactly the points where the derivative of f is 0, which, of course, makes sense, even though the derivative being 0 is something that makes sense on a Riemann surface, even if the value of the derivative doesn't necessarily make sense without some further thought. So, this is a well-defined set, and then you can check that it's discrete, because otherwise, by the same argument, if it wasn't discrete, then there'd be a point of accumulation, and you would get some kind of contradiction from that. Otherwise, contradicting the fact that the map is not constant. Okay, so what we want to say is the point is away from the set R. F is a local diffeomorphism, right? That's exactly what the inverse function theorem tells us, or our sort of neighborhood theorem. So we want to use this to kind of say that F is some kind of covering map when you remove the points R. But of course, that's not quite true, because if you just remove the points R and remove the points delta here, there may be points in X that sit over delta. So for that reason, we make the following slightly bigger set, which is R plus is just equal to F inverse of delta, which of course contains R. I'll draw a picture in a second to make this clearer. Okay, so the point of all of this is that because when we remove these points R plus, everything is a local diffeomorphism, or a local map, a local homeomorphism, and because we're proper, the preimage of any point will be finite, as we observed over here. So what we observe is that if we look at the map F0, which takes X minus R plus to Y minus delta, you should observe that this is actually in fact, it's a finite, given our assumptions cover. Okay? So in particular, what that means is that if we have any path in this space, then we can always lift it to a path here where our only choice is which preimage of the initial point of the path we choose, right? And the idea is that if we have a closed path here, we'll get a closed path up here if and only if the path we started with down here you could shrink it down to a point, right? So that's the sort of covering. Sorry, I should say that's not quite correct. So let me rephrase that. So the question is, if we have a closed path here, when does it lift to a closed path here, right? And clearly that's going to be related to, if you recall some sort of basic topology, that's related to the properties of the fundamental group of this space, right? So Right, so what I was trying to say is, of course, if we want to sort of understand such covers, at least topologically, right, we need to understand, we want to study say, well, conjugacy classes, but essentially subgroups of the fundamental group pi1 of, right, so just to say what pi1 of y minus delta is, so one way of thinking about it is to say fix some point y0 inside of, right, and then it's, you could think of pi1 of y, which is supposed to be the equivalence class of closed path starting and ending at y0 mod homotopies that fix y0. Okay, and then what you sort of end up showing is, because this you should check, but it's true this is connected, and so the choice of point y0 doesn't make a difference. So we sort of suppress it in the notation. So the observation is, of course, every cover gives us more or less a subgroup of the fundamental group, which has to exactly do with which loops, how a closed loop down here lifts to a closed loop up here. Right. And the point is, since this is a finite cover, that corresponds to this being a finite index subgroup inside of this group. And just to remind you, I don't really have time to go over this. Of course, something like pi1 of the complex plane is the same as pi1 of the unit disk is equal to pi1 of the Riemann sphere is always the trivial group. Right? That is to say, these are all simply connected. Similarly, something like pi1 of C star is the same as pi1 of D star. This is an abelian group, which is the integers. Pi1 of the torus is, of course, also an abelian group, which has two generators. And then, but of course, in general, for pretty much every other surface, you don't expect to get abelian fundamental groups. So just to give an example, something like pi1 of the Riemann sphere minus 3 points, right? This is the same as the free group on two generators, right? So this is a non-abelian and is significantly bigger than any of these groups. Okay. Okay. So we want to understand these subgroups, but in fact, there's a little bit more information encoded in the cover than just the subgroup of pi1. So to understand this. Okay, so suppose we look at f inverse, right, of y0, where this is some y0 is some point in which we want to call the point, say, right. Right, so this is a finite set. And what we observe is that for each homotopy class of loops in pi1 of y minus d, delta, right? So each class here, we have a lift. I mean, we take a path in the base manifold, and we lift it up to a path in the upstairs manifold, and we choose a beginning point, which is one of these points. We can see after we go around the loop which point we end up with, right? And the point is, for each loop we choose, and each base point we choose here, we'll get a different point. So what that should say is that if we do the lifting, a map from gamma, and to each gamma we associate an element, let's call it S sub gamma, which is an element of the automorphism group of this preimage of y0, which of course is the same as an element which we identify with the symmetric group on D letters, right? Everyone understand? So the degree is D, and that tells us that there's D points, right? So what we're supposed to think of this is that actually one of the pieces of information we get from a cover is that we have a representation, and the point is this will be a group homomorphism. So we have a representation from pi 1 of y minus delta. This is a representation, so a homomorphism, to this symmetric group on D letters, right, where we've identified the symmetric group of D letters with, say, the automorphism group of the preimage of some point. Right, I did maybe just to illustrate this with a very simple example, but it somehow encodes a lot of, I think, the idea. Let's just consider the map F that takes the unit disk to the unit disk, where we have z gets sent to z to the n, or z to the d, say. Okay? So what is delta in this case? Or what is r in this case? It's the origin, right? So r is equal to delta is equal to the origin, right? So we have a cover from an annulus, so we have F0, which takes d star to d star. And sort of pictorially, the way we're supposed to think of it is here's the base, so here's y, and here's delta. And then upstairs, we're supposed to have a kind of so for each point here, we have, say, d sheets here. And if we go around a loop gamma here, we're sort of going around the surface, say, up a point. Okay? I don't know if that is very helpful, but it's the best I can do. Right, but the idea is if we want to actually understand this automorphism group, you should convince yourself that the following is true. Right, so if in a sense we just take, if we identify the preimage of a point by sort of, we let's just take 1, say, and then we let the preimage of 1 be equal to e to the 2 pi I d, say, minus k minus 1 over d, where so now k is equal to 1 up to d, right? So we're taking the kth root and we're looking at this ordering. You should check that if you take one of the generators, I mean, you have to be careful with the orientation, but if you take one of the generators of, right, I mean, the pi 1 of this is z, so just take one of the generators which corresponds to going around once, that exactly what you're going to do here is exactly be a cycle which shifts everything up by 1 and the top one back down. Okay? So in other words, the representation, and in a sense, because everything's so simple, the only possible image of the generator is exactly a cycle inside of this automorphism group of length d. Right? You should convince yourself of that. Precisely because you want to have you have one generator, and it has to have the full. It has to be transitive, right? So the idea is that if we look at each point, if we apply the whole thing, everything goes up and the other one goes down. And so the remark, which is again from this construction, is that this action is transitive. Action is transitive. And what that means is if we look at the image of pi 1 under this map rho, then what am I trying to say? If we look at the image under rho, then that means that every that image acts transitively. Like, so we can take any point in the pre-image to any other point by choosing an appropriate path. And the way to do it is you use the fact that upstairs x minus r plus is connected, right? So I should make an assumption that x is connected. I should have written that. But you draw a path between them, and then you put it downstairs, and that's exactly the homotopy class of that path is exactly the guy that will give you the automorphism that will connect the 2 points. Of course, it's not transitive if the upstairs is not connected, because we could, of course, just include another copy of the disk, right? And if you had another copy of the disk, there's no way to get from this point to this point. You'd have to kind of add some way of gluing them together, which would be out here somehow, perhaps, right? I don't know if that makes any sense, but so let me just try and summarize what the information we get from the cover is. Okay, so to sort of summarize, right, so associated to this function f, we get an integer. This is the degree. 2, a discrete set delta inside of y. So this is the image of the branch points. And then 3, we get a transitive representation rho that takes the fundamental group of pi minus delta to the symmetric group on D letters. Okay? Okay, and the remarkable thing is that actually this data entirely determines f up to equivalence. So that's what's known as Riemann's existence theorem, which I think is maybe probably the first thing that's really, I think you should really take to heart as a very kind of interesting fact. So this is okay. All right, so given y, a connected Riemann surface, delta subset of y, a discrete set, and a transitive representation rho that takes pi 1 of, given a connected Riemann surface, a degree, an integer d, a delta. So you're just basically given this information. So y backslash delta to SD, then this implies there exists a unique Riemann surface X and holomorphic map so let's call this information sort of the monodromy of the map, because it sort of tells you it has to do with how the behavior of lifts of curves downstairs to curves upstairs. So whose monodromy is the given data. Okay, so this is really, I think, a very remarkable result, which, I mean, does a lot of things for you. So one of the things which it does, which is very nice, which maybe I have about a little bit of time, so I'll try and talk about. Right, so remember back at the first class, I said there was sort of a question of, well, if you're given a topological surface, why does it admit, why can you think of it as a Riemann surface when it's oriented, right? And the homework you had, the exercises you had, you could do it by sort of showing there was a kind of analytic type argument by showing there was a Riemannian metric and then looking at the conformal class of that metric and proving that that gave you a holomorphic atlas. But actually, this gives you a way, at least for closed surfaces, to give a kind of topological argument to why every closed surface that's oriented has a Riemann surface structure. And actually, it kind of indicates certain things about how one might start to parameterize the space of all such things. So what's the idea here? And again, I'm afraid I'm going to have to draw some pictures, so it might be totally meaningless. But OK, so let's suppose we start with, let's say sigma is just some genus G surface oriented closed surface. Right. And let's draw it, let's try and draw it symmetrically as follows, which is let's just draw, let me draw one more genus. All right, that doesn't make any sense. OK, so here's a genus 2 surface. So here's G equal 2. OK? And let's look down here. So notice that, just thinking of this as an R3, we have this rotation map where we rotate around, say, the z-axis, right? So notice, what are the fixed points of this rotation? So the fixed points are exactly these points, right? So if we delete these points, you should convince yourself that this rotation is a kind of is a free action, and in fact has this strongly free property we discussed before. So suppose this is 180 degrees. So if you take the quotient by this identification, what do you get? Right. So this guy gets identified with this guy. You should convince yourself that the quotient is OK, that's not quite right. Right, so there's 1, 2, 3. I obviously have trouble counting. OK, so, but notice this is S2 with now 6 points removed. Right? These are 6 points. OK? So what you should convince yourself, I mean, the point is this is this map F0, where you remove these 6 points, is a map from the 6 times punctured genus 2 surface to the 6 times punctured S2, right? And the point is, this covering map, we can just recover from this all these invariants. So the degree is 2. You should convince yourself of that. You get this discrete set, which is exactly these 6 points. And you have a transitive representation, which is essentially if you go around the end, right, I mean, that's going to correspond. You have to figure out what it is, but it is a transitive representation. So by the Riemann existence theorem, if we just think of S2 as the Riemann sphere minus 6 points, we can then pull back. And of course, you should, by the Riemann existence theorem, that tells us that there actually is a holomorphic structure on this guy, so that we have a map here on this genus 2 surface, which maps holomorphically onto S2, and it sort of has branch points exactly at these 6 points, right? So that actually, and we can make this true for any genus. I mean, the argument works the same. So that actually proves that we have a Riemann surface structure on the genus 2 surface without, I mean, just using this Riemann existence theorem. The other thing that one can observe is, of course, that one can take, for instance, if you wanted to, one could take one of these marked points of S2 to be infinity, and this would allow us to construct this shows that on, say, a genus 2 surface, we definitely have a meromorphic function with an order 2 pole, right? So one of the things you should start to think about, though, is how many, right, it's not so hard to kind of say, I mean, you can think about, we know what the conformal automorphisms of S2 are. They're just the Mobius transforms. And one of the homework problems is to show that a Mobius transform can take any 3 marked points to any other 3 marked points. But that means that once you have more than 3 points, then you have conformally inequivalent surfaces. So that actually means that by this construction, once one fixes the conformal structure on S2, as one varies the points, then one's going to vary the complex structure up here that one gets. So that is actually another way of seeing that there has to actually be lots of complex structures. So probably next week, we'll do this very in detail in the case of the torus. But I want to remark that this is something that can happen. The other thing is, and I'm basically out of time, but one thing that, again, I have on a homework that hasn't quite been posted, the exercises, but notice that sort of the deck transforms of this cover is exactly this rotation by 180 degrees, right? And what this means, you should convince yourself that actually the deck transforms act transitively on this SD. But you take a preimage of a point, and you have 2 points, and the deck transforms interchange them. So that's to say it's a regular cover. So you should try and see that actually there can be lots of examples where you don't have a regular cover by sort of playing around with these representations. And that actually gives you some kind of interesting things about why you might have Riemann surfaces that it turns out that have very few kind of conformal transformations of themselves, right? I mean, you notice that in this case, I mean, you should convince yourself if you do this very symmetric, this will have lots of symmetries because of the, if you have a symmetry down here, so if these 6 points are in a symmetric configuration, they should be symmetric up here. But anyway, I'm kind of blathering. But so let me just stop here because I think we're out of time. And then maybe next time I'll give a sketch of the proof of this, which is really just uses this fact that somehow when you have locally, you have these very simple descriptions, so you can just use this picture to glue in a disk to kind of fill everything out. And then I'll start with talking about some calculus on Riemann surfaces, which will give us the sort of analytic language we need to get to the uniformization theorem. OK, so I'm going to stop here.